Hello everyone. In this video, we will discuss about boranes. In this video, we will discuss the weight rules for the determination of shape of different borane clusters. We will also know what are the various applications of boranes, and we will take one of the common example of boranes, that is diborane, and for that we will also discuss the structure and bonding of diboranes, and furthermore dear, what are the various applications of diboranes in different areas? Now let us discuss what are the learning outcomes of the present video. After studying this video, you shall be able to understand weight rule for the prediction of shapes of boron clusters after calculation of SEP, that is skeletal electron pairs. We can understand the what type of shape of boron molecule. We will also know the various applications of boranes in different areas, and you can also explain the preparation properties and structure of diborane, which is the one of the most common example of boranes compound. And you can also know the various uses of diboranes in different area in the present. Now come to weight rules. Sometimes it is also called PSEPT, that is polyhedral skeleton electron pair theory. And in chemistry, polyhedral skeleton electron pair theory, it is given to count the electron numbers for prediction of shapes of clusters such as boranes and carbonates, etc. And sometimes it is also called as weight rule or weight chemistry. For this, Kane Wade developed, that is the Kane Wade, developed a method for the prediction of shape of borane clusters. However, it may not be used only for boranes, that can also be utilized for some substituted boranes like carbonates as well as other classes of different cluster compounds. And weight rules are also used to predict the shape of boron clusters by calculating the total number of skeleton electron pairs, that is SEP, which is available for cluster bondings in different clusters. And the general methodology which can be utilized for calculation of SEP, which is given by weight, that is, it can be as follows. First, determine the total number of valence electrons from the chemical formula. That is, we can take 3 electrons per boron atom and 1 electron per hydrogen atom. And the second, then subtract 2 electrons for each BH unit, or 3 electrons in case of CH if we are having carbonyl cluster. Similarly, divide the number of remaining electrons by 2 to get the total number of electron, that is SEP, skeleton electron pair. So after that we can see what type of shape can be possible on the basis of available number of SEP electrons for that cluster. Suppose if we have a closure structure, that is formula is BnHn2 minus, if we are having skeleton electron pair, that is SEP is equal to n plus 1, then that cluster will be in the category of closure class. Similarly, if we have nido class, that is BnHn plus 4, if we are getting the value n plus 2 SEP, then that will come into the category of nido class. If we are having general formula BnHn plus 6 and we are getting the n plus 3 SEP electrons pair, then we can say that it comes under the class of arachno. If we are having general formula for clusters BnHn plus 8 and we are getting the number of electrons pair, that is SEP n plus 4 after calculation, then it will come in the category of hypoclass. And at last, if we are getting n plus 5 SEP electron pairs whose formula is BnHn plus 10, then it means that it comes under the class of clado clusters. So this is the how we can calculate the predict the shapes of different clusters like boranes and carbonates, etc. Now let us take some examples through which we can calculate the number of electron pairs, that is skeleton electron pairs in some borane molecules so that we can predict the shapes of borane clusters in respective molecules. So for example, we are taking the example of B5H11. As we can see in this case, we have 5 number of boron, 11 number of H atom in case of B5H11, and according to various rules we have discussed that for one boron atom we have to multiply by 3 electron, and for one hydrogen atom we have to take 1 electron. So in the such step, when we will calculate the total number of valence electrons in case of B5H11, so we will have 5 into B plus 11 into S, that means 5 into 3. 3 we have taken for number of boron atoms, multiply by 3 electrons for each boron, that's why 5 into 3, plus 11 into 1. 1 we have taken for each hydrogen atom, we have taken 1 electron, that's why total number of electrons in this case we have 26 valence electrons. Then after that, number of electrons for each BH unit that we have already discussed, it should be equal to 2. That's why we have 5 BH bond in case of B5H11. So we have to multiply by 2 for each BH unit, that is 5 into 2. Then we will get the value of 10 for each BH unit. Now, after this, we can calculate the number of skeleton electrons by subtracting 26 minus 10. Then we will get the value of 16 electron in case of this one. Now, how we can calculate the pairs? As we know that for one electron pair, we have 2 electrons. That's why by dividing 2, we can calculate the number of skeleton electron pairs, that is 16 divided by 2. We will get the value 8 pairs. As we know that n is equal to, that is the number of boron atom is present in case of boron cluster. Here we have 5 boron, that's why we have n is equal to 5 value. Then after that we will get that we are having n plus 3 electron pairs, that's why it belongs to arachnoid cluster because n plus 3 is equal to arachno, as we have discussed in the previous slide. Now let us take another example for B5H9, that it can be closo, it can be of nido, it can be of arachno, or it can be of hypocluster. How we can identify this? Then it can be calculated by calculating the number of scattered electrons in this case, through which we will get what value is coming. Then we can identify whether it is closo, nido, arachno, or hypocluster category. For this, when we are calculating the total number of valence electrons, we are having 5 boron, that's 5 into B. We have 9 H, that's 9 into H. For each boron, we have multiplied by 3, that's 5 into 3 we have taken. For each H, we have multiplied by 1, that's why we have taken 9 into 1. So total we are getting, after getting this one 15 plus 9, we are getting the value 24 valence electron in case of B5H9. Then we have to calculate number of electrons for each BH unit. As we have discussed, for each BH unit, we have taken multiply by 2. In this case, we have 5 BH unit, that's why we have multiplied by 5 into 2. Then we are getting the value 10. That is for each BH unit, number of electrons. Now, after that, how we can calculate number of skeletal electrons? That is, when we are subtracting 24 minus 10, then we are getting the total number of electrons, that is equal to 4. That is the remaining electrons, skeletal electrons. Now, how we can calculate the skeletal electron pairs? It is equal to divide by 2, that is 14 divided by 2. Then we will get the 7 pairs of SEP type, which is for this particular B5H9 molecule. Then as we know that we have n is equal to 5 because in B5H9 we have n is equal to 5, that is equal to boron atom. In this case we have 5 boron, that's 5, n is equal to 5. Then remaining is 2, so we are getting the value n plus 2. N plus 2 is for the class nido. That's why we can say that B5H9 cluster is categorized in the category of nido cluster type. Let us take another example in the form anions, that is B4H42 minus, whether it can be closo, nido, arachno, or hypocluster, that we can calculate the SCP number, then through which we can identify whether it will be of closo, nido, arachno, or hypocluster type. Let us take example. Number of electrons for each BH unit we have taken because we have 4 BH, 4 into 2, that's why we are getting the 8. Similarly, we have 2 minus charge, so number of charge is equal to 2. Then it means equal one charge equal to one electron. That's why we are here taking the two value because we have two minus charge. So we are taking two electrons. Total electrons how much? 8 plus 2 is equal to 10. Then divide by 2, number of SCB value we will get. 10 divided by 2, that is the 5 pairs. Now in this case we can see that n is equal to value is equal to 4. Why it is 4? Because in B4H4 2 minus we have number of boron atoms is equal to 4. That's why we have put the value n is equal to 4. Then we will check. So remaining is only 1. So we can say it will give the n plus 1 value that belongs to the Closure cluster according to the weight rules. Let us take some more examples for calculation of number of SCP through which we can predict the shape of different clusters of either boranes or carboranes. For B5H9, we have already calculated in the previous slide. For that, we are getting the value of n plus 2. That means it comes under the class of nido cluster. Now let us take another example, that is B2S7 minus. In this case, we have, because we have two BH units and we have discussed that for each BH units we have to take 2. That's why we have 2 into 2 is equal to, we are getting the 4 number electron. Similarly, we have here remaining is the only 5 electron. So for 5 electron, 5 hydrogen, we have taken the 1 electron from one H atom. That's why we have taken 5 electron in this case. And its overall charge is minus 1. For 1 minus charge, we are taking the 1 electron. So total number of electrons, that is equal to the 10 electrons. That means it is equal to the 5 pairs because we have in 1 electron pair, we have 2 electrons. That's why it is giving the 5 pairs. Now calculating by this one, we know that in this case we have number of boron atoms is equal to 2. That's why we have taken the n is equal to 2 value here. And when we will calculate with these electron pairs, then we will find out that remainder will be 3. That's why it belongs to n plus 3 category. That means it is the shape is of type arachnotype clusters for B2S7 minus. Let us take an example, which is a class of carboranes. Carboranes are the metal clusters which is made up of, along with the boron and hydrogen, they are also consist of carbon in molecule. Here we can say it is the formula for carborane C2B10S12. So along with the boron and hydrogen, that also consists of carbon. So that's why they are referred to as carborane instead of borane. Now let us see how we can calculate. As in case of weight rules, we have discussed for each CH unit, we have to take 3 electrons. That's why we can say here 2 CH units are there. So for 2 CH, we have taken here 6 electrons because 2 into 3 is equal to 6 electrons. Similarly, here we have 10 BH units. For each BH units, we have taken 2 value. That's why for 10 BH units, we have taken 20 electrons. Total number of electrons equal to 26. It means equal to the 13 pairs for 13 years because we have 2 carbon atom and 10 boron atoms. So n value is equal to number of carbon and boron in case of carbonate. That's why we have taken n is equal to 12 in this case. But when we will compare with the 13 pairs, we will find that 1 is remaining. That's why we are getting the value of n plus 1. N plus 1 is categorized for closure clusters. So we can say that C2B10S12, it comes under the category of closure type cluster. Similarly, if we are taking another example of carborane, that is C2B9H112 minus, for each CH unit, in this case we have 2 CH, that's why we are taking 2 CH equal to 6 electron, and we have 9 BH units. For 9 BH units, we have taken 9 BH 9 into 2, that is given 8 electrons, and overall charge is 2 minus. For each charge we are taking 1 electron, that's why we are value is the 2 electron. So total electron 18 plus 6 plus 2, that equals to 26 electron. It means that is equal to 13 pairs of electron pair, that is SCP. For in this case, we have 2 carbon, 9 boron. So total number of value is equal to n is equal to 11 we are putting here. And when we are comparing with electron pairs, 2 is remaining. That's why we are having n plus 2 value for this type of cluster. So we can say that this type of cluster, it comes under the category of nido class. Similarly, we have calculated for different types of substituted and different class of clusters for using weight rules, in which class they are categorized like This one is under category of closo. This one is for closo. This one is also closo. That comes SB9H11 comes in the category of nidotyl clusters. Now come to the applications of boranes. Boranes can be utilized in different areas, out of which we have discussed here following applications, that they can be utilized as the adducts in the form of BS3 in organic synthesis, that is for hydroboration reaction. As we can see here, it can be have taken alkenes. When it is reacting with the BS3 and it is undergoing the hydroboration reaction, then last product we are getting in the form of alcohol. So this is for this hydroboration reaction. W.S. Brown, he has received the Nobel Prize for his work in the contribution of boron chemistry in organic synthesis for hydroboration reaction. Then, boron hydrides can also be studied as a potential rocket fuels, yeah, we can say rocket propellants, that can be also utilized for automobile purpose. Boranes can also be utilized as ligands in coordination chemistry, and borane can also react to form heteroboranes, like if they are reacting with the carbons, so they can also produce the carboranes along with the boron and hydrogen, and they are also having metalloboranes. If boranes they react with the some metals, so they will form the metalloboranes type clusters that contain boron along with the some metal atoms. Then BS3 can also be act as a reaction intermediate in the pyrolysis of diborane to produce the higher member of borane clusters. And boranes can also be utilized in case of medical field for the drug delivery system. Yeah, we can say in the form of nanomedicines, they can also be utilized where some important role. And they also can be utilized as we have discussed in the machine lab. They have prepared a new blue laser when they are putting the light on the solution of these type of boron clusters, then they are producing the blue color laser light. That is the recent discovery in case of boron chemistry. Now come to the diborane, which is the simplest known boron cluster known in the literature. Now, diborane is basically a chemical compound which is mainly composed of boron and hydrogen atoms, and which is having a molecular formula that is B2S6, and it is the simplest known borane cluster which is known in the literature. But lower borane molecules are highly reactive in nature, because when they come in contact with the air, they can easily catch fire. So for the safe full synthesis of these lower members, as we have in diborane, the father of boron chemistry, that is Alfred Stock, he used the chemical glass vacuum technique, yeah, we can say Stock apparatus, for the safe full synthesis of lower membranes of borane clusters, as in case of diborane. This is the three ball and stick model for diborane molecule. In this case, pink color balls are representing the two boron atoms in case of B2S6, while these white color balls are representing the H atom, which is bonded with these two boron atoms in case of diborane. So this is the ball and stick model for diborane molecule. Diborane is also one of the simplest boron hydrides known to us, and it is only stable borane which consists of two boron, which is frequently called as diborane because it is having two boron atom in it. And diborane is also an electron deficient molecule because does not form the normal type of covalent bonding, because it is having only 12 electrons in this molecule. That's why it is also an electron deficient molecule, because it could not complete the, as in case of C2S6, we cannot make the normal covalent bond in case of diborane. The other names of diboranes are boroethane, diboron hexaidide, etc. Now let's discuss some methods through which we can prepare the diborane metal crystal. The first method is that it is the simplest boron hydride that can be prepared by treating boron trifluoride with lithium aluminum hydride in diethyl solvent, then we are getting the diborane molecule along with the some other products. Second method is that in laboratory, diborane can be prepared by the oxidation of sodium boron hydride along with the iodine, then we will get the diborane molecule in laboratory. For industrial scale, it can be prepared that we can treat the boron trifluoride along with the sodium hydride at 450 Kelvin temperature, then we will get the diborane molecule for industrial purpose at large scale. Now come to the different properties of diborane. First is that diborane is basically colorless, highly toxic gas which can boil at 180 degree Kelvin temperature. And diborane, it can easily catch fire when it comes in contact with the air that we have already discussed. For lower members of borane clusters are they are highly reactive in nature because diborane is the simplest known boron hydride cluster, so it can easily catch fire when it comes in contact with the air. It burns with the oxygen, and this reaction is exothermic reaction that release the large amount of energy when it oxidizes along with the air. It gives such a large amount of energy during this process. And third property that it can be readily hydrolyzed by water, that it will be produced the boric acid that can be utilized for various purposes. These are some more properties of diborane. With Lewis bases, diborane first undergoes the cleavage to form the borane, which then reacts to form the adduct, that is BSC.NMe. Similarly, with ammonia, that is here, an addition product, that is BH2 NH3 twice plus BH4 minus, it produced, which on further heat treatment at 473 Kelvin, it produced the new class of compound that is known as Borasol, that is B3 and 3S6. Yeah, it is also known as Boragine, which resembles with the benzene type structures. On the basis of that one, it is also referred to as inorganic benzene. Now let us discuss what is the structure of diborane. X-ray diffraction shows that these are the following structures of diborane molecules. As we will compare when it along with the ethane molecule, that is C2H6, we will find that in case of boron, where atom when it is in the ground state, we are having 2s2 2p1 type of electronic configuration. When it undergoes in the excited state, we are getting the 2s1 2p2 type of electronic configuration in the excited state. On the basis of that, we can say that boron can form the it can utilize the sp3 hybridized orbital in which three orbitals are half filled, and they can make a two center two electron bond with the three other hydrogen atom, but one atom is remains vacant. That's why on the basis of that one we can say that boron diborane is electron deficient in nature. As in case of ethane, all the four orbitals in case of carbon, they are also utilizing the sp3 hybridized orbital, but all the four orbital in excited state they are half filled. Yani ki in case of C2H6, they can make 4 CS type bond, but in case they are only utilizing the 3. Here we can see this is the structure of this one. Yeah, we can take example of orbital diagram of diborane. Here we can see that these four atoms, which is shown in the gray color, these are H atoms, which are referred to as terminal hydrogen atoms, while these pink color hydrogen atom, which is represented above and below this one, in between this one boron atom, these are referred to as bridge atom, which makes a bridge between two boron atoms, this type and this type. So these are also involved in the making of banana type bond in diborane molecule. We have two banana bond in diborane molecule. Here we can see that this boron it utilizes sp3 hybridized orbital which makes head-to-head overlap with the 1s of this terminal hydrogen. For that, it makes the this BH bond. Similarly, that can also utilize. So we have, in case of diborane, we have four normal type of two-centered two-electron type bond, covalent bond, which is as usual in case of ethane. But if we will consider these here, this boron atom, it utilizes the sp3 and 1s of H and 1s 1 sp3 of this boron atom. So they are head to end overlapping takes place between the sp3 of this boron, 1s of this hydrogen, and sp3 of this boron atom. So they are making in such a way that this is the electron. This is also having one electron, but this sp3 orbital of boron remains vacant. So we can say that they are forming the two electron three centered bond. Two electron, how we can say that? One electron from the 1s of H and one electron from this sp3 orbital, that is half filled. So they are making the two centered three three-centered two-electron bond. Similarly, if you are taking another banana bond, here we can say that this boron, it utilizes the sp3 orbital which contains one electron. That makes the head-to-head overlap between the sp3 of boron, 1s of H orbital, and vacant sp3 orbital of boron. That will also make the three-centered two-electron bond. So we can say that there are two types of banana bonds in this one, and these centered hydrogen are also referred as bridge hydrogen atoms, or all the four hydrogen which are terminal, and these two boron atoms, they are in single plane, while the two middle hydrogen, that is referred to as bridge hydrogen atom, they are residing above and below this plane. This is the structure of diborane, because in diborane we have only 12 electrons possible in different bonds. We can say that diboranes are of electron deficient in nature. In this slide, we have shown the another structures of diborane, which represents the two banana type bond that can be possible between BHB BHB bond. Here St represents the terminal hydrogen atoms which are in plane with the two boron atoms, while Hb represents the bridge atom which makes a bridge between two boron atoms. So these two atoms are of bridge atoms. And in this case, banana structure, we can see we have two electrons. As we discussed, one electron is from sp3 hybrid or a boron, and one electron is from 1s of hydrogen atom, which is a type of bridge hydrogen. So they forms the three-centered two electron type bond, which is categorized as banana bond, which is a special type of bond. Similarly, the second type of banana bond, which is also three-centered two electron bond, and these four are the normal covalent bond type. That is the one electron from sp3 hybridized of boron, one electron from this 1s of hydrogen. When they are doing the head-to-head overlapping, so they are forming the two-centered two electron type of normal bond. So here in case of diborane, we have four normal type of two-centered two electron bonds can be possible, and this is the another structure which is represented by ball and stick model. Here green color balls are representing for the two boron atoms present in case of diborane, while gray color balls represents the H atoms present in this case. So out of this, these four are terminal hydrogen, while in the middle one they are representing the bridge hydrogen atom in case of this one. Because in diboranes we have only 12 electrons, that is 2 electron less than the maximum required for. That's why it is also referred to as electron density. These are the uses of diborane in different areas. Diborane, it can be as utilized as a chemical substance which has large number of applications in different fields, in which some of which we have mentioned here. Diborane can be utilized as a rocket propellant, or we can say rocket fuel, for utilizing the rocket technology. It can be also utilized for the manufacturing of glass, which is the type of boro borophosphoresilicated type glass. that can be utilized for the glass making industry. In most of the chemical reaction, it can also utilized as a reducing agent, and that can be also utilized as a catalyst and rubber vulcanizer in the polymerization reaction. And it is also utilized as a doping agent in the manufacturing of the various semiconductor devices. So these are some of the uses of diborane in different areas. In the present video, we have discussed what is weight rule, how we can identify the shapes of different metal clusters like boranes, carboranes. We have also discussed like what are the various preparation methods, property structure of diborane molecules, and what are the different applications of the diborane in different areas of fields.